Okay, so I'll start with a question for the panelists, and then we'll open it up, and then I can ask some more questions if we need to. So maybe can you just talk, like, for each of you, this is a question for each of you, talk for a couple minutes about how you think machine learning and AI are going to change your field, whatever your field is. I don't know, Manya, you can, if it's networking or optical networking or systems or whatever, how do you think it's going to change your field in the next 5 years? And do you think it's underrated or overhyped? Like, is machine learning, like, does it really matter, or is it like, is it really as big a deal as everybody says it is? So we'll start with Manya.
Okay. I think machine learning is neither underrated nor overhyped. It is undeniable that machine learning is changing our world, and there are many challenges that we need to solve. But I think the marriage between machine learning and optimized systems is really the key to enable future applications to not only be about making it easy to perform a small task, but also integrate machine learning into our day-to-day life. In particular for networks and systems, what I think will happen in the future is that we will be able to solve complex systems problems with the help of AI, and on the reverse side of it, we will be able to advance the machine learning system with innovations in the networking domain. I'll just stop here.
Mohammad?
I think we are past peak hype in sort of, so not in LLMs. We are that's a different story. But sort of in generally, like in applying machine learning to, systems problems. I think we are starting to kind of get a handle on where things work and where maybe things don't work so well. As Tim, for example, talked about, you're starting to see things being deployed. That's not something like we could have said like 5 years ago. That was maybe peak hype, sort of, in this space. In terms of sort of what it will change. I think the kind of work that you're seeing right now that, we've talked about of taking kind of components that we've had in systems and enhancing them with machine learning, doing instance optimization, using kind of like characteristics of the data and the workload that we're seeing to, I think that that's increasingly, in my view, that's becoming kind of mainstream, actually. In all of systems, I say like there's, in every area, there's always like a lot of things that you just have to make decisions about that used to be sort of, human design heuristics. And I feel like human design heuristics are kind of getting replaced with like machine discovered heuristics in some sense, and I think that trend will just continue. There's a kind of maybe a bigger opportunity which excites me, but I don't know exactly how it will go. Is that where AI basically creates kind of new capabilities, like new kinds of systems that we could not have built before. Some of the video querying that you're talking about is like that, because we now have these models that like understand video, and certainly with language and LLMs and kind of we're seeing applications that we couldn't have imagined before. So personally for me, that's maybe like what I'm most excited about in the future is kind of seeing what kind of new systems we can build, and that would be enabled by this.
Yeah.
So for machine learning for systems, I'm with Mohammad. I think like it's like beyond the peak hype, which was like probably like 2, 3, 5 years ago. The new hype is clearly generative models, and Gartner is saying it's overhyped but also real. And I think there's some truth to it because like it changes the way people interact with systems, like really in very unique new ways. And I think I think this area is pretty interesting. Like if you think about that, like for example, if you query data currently, everybody's using SQL, but natural language is like becoming a thing. And that for the first time ever, it's kind of interesting how it changes also the system design for it, because like now, like there are other problems you suddenly have to deal with if this becomes the new interface for accessing data, or like creating visualizations, or creating a question answering system. It's quite a big change.
Cool. I mean, I think I sort of agree with Mohammad that to me, what's really exciting about all of these things is that they've created this new, like this awesome new capability to, like, I feel like many of us in like my field, which is more data processing, there's been this, like, people, every couple of years, somebody's like, oh, we're going to build a system that, like, whatever, a database of videos, and we're going to let people query metadata about the videos. Or there have been these, like, kind of like image search systems going back to, like, the early 2000s that, like, never really worked very well, right? Or this text stuff. I mean, people have tried to, like, do natural language interfaces for querying. This has been like this, like, for, every 3 years for the last 20 years, probably longer than that. Arvind it's probably been 40 years, right? People have proposed to build systems that do these kinds of things. And now it actually works. I mean, it's just shocking how good it is. I mean, you can literally go on ChatGPT and say, right, here's a database, write a SQL query to process this, and it can do it. And it's kind of, I mean, if you've been in the field, it's kind of flabbergasting that it can do it, and it can do it so well. And on top of that it has progressed so quickly. I mean, I think if we had this panel 2 years ago, I would have said, oh, it's pretty good, but it's never really going to be able to capture all the nuances of SQL and all this. No, it's like, I mean, the thing has gotten so much better so fast that it's just, so that's a really exciting capability, I think. On the other hand, I also am not, I'm not quite sure. I mean, it does feel somewhat overhyped. So I don't know. What I'd like to do is, anybody in the audience have a question they'd like to ask? I mean, a big question, or we've got 4 or 3 anyway. I'm not sure about myself. Super smart MIT professors up here who spend their life thinking about systems and machine learning. So what would you like to know? And yeah, I can, if you can. There's some mics back there, so go stand up at the mic and ask, if you don't mind. Just right there, there's a, yeah. Here's Dina. Time.
Okay. So this is a question for everyone. It's general. I don't know how deep it is. I certainly found it interesting looking at machine learning or an AI in specific domains. And I'd like to return to where Sam began with the large language models and ChatGPT, and whether what seems to be the case now is advances to ChatGPT 4 or 5 is all in the context of scale, more data, more weights, more processing. And it's clear that can't continue. There must be some other insights we will need to go something deeper in understanding than just scale. And so my question is, with your experience in particular domains, do you have any insights how we could do better with large language models other than scaling?
I'll start, and then I'll let other people say more stuff. I mean, one thing that occurs to me, and this isn't a very deep answer, but clearly a lot of the art of these models is in the judicious selection of the data that they're trained on. And I actually think that's a very interesting question. I was talking to a person who worked at worked on Alexa a few weeks ago, and he was talking about how they had tried to, of course, Amazon wants to build specialized interactive language models for Alexa, right? And it can't quite be the same as ChatGPT because ChatGPT is like, it's very wordy and it, give these big, it needs to be these kind of succinct answers that you'd get out of your, Alexa device. And so they were training it on some data set, fine tuning it on some data set that they had acquired from Alexa. And they found that after they did this, that it turned out their training data had been collected from a whole bunch of people in Seattle. And so the thing gave answers that were super Seattle specific, like it would, I don't know, talk about the Space Needle or something all the time, right? And so like getting the training data right is actually a really interesting and hard problem. I actually think that's something where there probably are some interesting systems challenges around it. But I bet other people can talk more about this question.
I can add one thing. So, of course, the computation is one axis. The other axis recently working on and got interested in is how can you use synthetic data to learn. So the generated data, in fact, in one recent submission that we have now, we showed that you can get higher accuracy learning purely from synthetic data, from generative model, than the actual data. And so the reason why I'm mentioning this is that one thing about using these generative model to generate the right data for the learning, to generate the hard examples. Because like your standard data may not have enough of certain cases, but your generative model may learn how to generate more of those examples. So let's say that you are trying to learn like how to drive, for example. So examples of accidents are very important, or near accidents, but those are very few examples in any data sets. But a generative model that you can infuse this interactive learning with it to generate the right set of examples to complement your data can be more powerful and help the next generation of both representation learning and also generative models as well. So it allows the person to be part of the learning and the generation of the data.
Although there's sort of a way in which this becomes like biased, right? Like if you only train the data on synthetic data, then it only learns the things that it already knows about, and so it's like an echo.
If you know on how to create the synthetic data, yeah.
No, so this is what I used to think, but I think that the point that I'm trying to highlight here is the power of active learning. Like remember, like there is this concept of putting the human in the loop, and the human actually can enter the loop to correct those biases, because with a generative model, the human is creating the prompt in a particular way. So that to enter into that loop and change that bias.
So maybe it's a little bit of a controversial opinion. I actually think size does matter in this particular case. And it's just like there was this whole trend of trying to build specialized models, and there's a whole bunch of open source work, also Llama and Co going on. What we normally found right now when building actual applications we are rolling out, also friends at Microsoft saying the same thing. The best strategy right now is use the largest, best model you can get your hands on, and then build some type of RAG infrastructure around it. Not even do refinement or any of that, because first of all, you cannot afford it. Second, then hosting and serving these models becomes a huge issue. So everybody is more or less doing the same. Get the best models you can, serve them as efficient as you can, and then build RAGs around them. This is the current trend. Will that continue like that? There is some argument to be made it will. Because the good models are so much better. And if I give them the right context, they get even better. And what all of the models are also improving is the context length. It started with 100 tokens or something. Now they're at 10,000, 20,000. And the token context matters so much. Yeah. That's at least what we observe.
Yeah, I think that's very interesting. I think it's interesting. If you look at sort of the kind of things that a lot of us do in sort of applying ML to systems problems. It's viewed that there's very general models, very general search strategies or sort of very general solutions to these optimization problems, that largely is not the way we, like, it's not the solutions that mostly succeed in kind of the, applying ML to systems. There's a lot of structure, and if you sit and you think about a query optimizer, or you think about a video codec, if you can exploit that structure, you'll definitely like have things that are much more efficient, and in a lot of cases you'll have things that are more robust, that do perform better, that generalize better. So that's when you go to special domains, that's kind of what you see. But in things like language models or vision sort of understanding, I think in those fields, the generalists have won, very handily, in the last 20 years. All these people that try to use statistical methods about language structure, that kind of work is disappearing, right? And now you have a transformer model trained to predict missing tokens. It learns all that structure, and it does things that you cannot sort of embed your domain knowledge into in any way. So
to put it in different ways, just like if you have, let's assume you're producing certain parts and you want to check them for errors. If you have such a narrow domain where you know all the error types, all the images, how they look like, I still believe that one you probably can build a specialized model because it's so narrow. Right? In the moment, it's just something which just touches natural language for querying data or video processing, where there's a lot of common sense in there. These large language models, if they're general purpose, they win right now by far.
Yeah. So at least I guess I would say, I think if you look at the trend, I absolutely agree with them. I think the trend has been general search, general learning techniques that you don't sort of embed a lot of your bias into have won, and that often has to do with scale of data and sort of architectures. If there is a change in that trend, I think it will also come from just finding out how to improve those general intelligence algorithms. It's kind of not from maybe again human insight into the structure, as far as I can tell. That's sort of I'm not an AI person, but my understanding is I feel the generalists are winning by a large margin right now.
Let me add a quick story that I just heard a few weeks ago when I was in the Silicon Valley. The story goes as, what do you do if you've designed a DNN model that performs poorly? Say the accuracy is bad. Most of us, when we are asked this question, we say, well, debug the model, or debug the data, or feed a different type of data. But as this story goes, it turns out that the conventional wisdom right now is to make the model larger and feed more data into this, and the problem goes away. Now, this is maybe the trend right now, and I kind of sense that your question is, how far can this go? Mm-hmm. I don't know, but it's been quite positive impact and a positive response, and it's really hard to think about how to walk back from this scaling technique.
I guess the question is, one question that is not totally clear in my mind is how, and maybe it gets to this question of the generalists winning. I mean, yes, they've won, but they've won in these domains where there's an infinite amount of training data available, right? So in a non-infinite training data scenario, of which a lot of the types of problems that we're talking about are, these query optimization problems, for example, right? Or we have this startup company where we, one of the things we do is process crash traffic data and building models to detect if there's a crash in sensor data. I mean, we're in a very data sparse setting. We just don't have that many examples of crashes, to Dina's point. So, it's, will these architectures win in those data poor settings? I think, I don't know. Again, I'm not a machine learning person either. But.
Mm-hmm.
So Arvind wants to ask something.
I think just listening to it's very clear that machine learning is here to stay. I believe all systems you're building is playing a crucial role, right? And there is no going back because it's data acceleration and you're streaming the system. It's essentially automating something that we use for heuristics or this and that. Now, I'm wondering if generative models will also have same kind of effect at the next level, that you will be automating something right now which we are not automating, right? We can apply our own intelligence.
Yeah, so maybe I'll just restate the question for the recording. So I think the question is, will generative AI have a similar transformation or to systems in the way that the sort of machine learning techniques that we talked about today have allowed us to, for example, replace human-guided optimization with algorithm-guided optimization. So it's like, what are the implications of generative AI for the design of systems? So interesting.
I mean, there is the obvious one that it's happening now, which is like basically taking the role of programmers, generating code from people who really don't have much programming experience. That's code that actually can build large systems. So that is definitely on the horizon.
Go
ahead, please.
So I normally always think about personas using a system, and each of them I think is impacted by generative models nowadays. You have the administrator of a system, and they are getting now chatbots to help them debug, set something up, get suggestions how to run the service, popping up like notifications if something is not online. So you get like administrator help. Then you have in the case of data systems, you have like analysts. They are now writing natural language queries. They are using natural language to create visualizations. So that whole behavior is changing. You have developers, to Dina's point, right? Like it's also changing. You have like tools, co-pilots and co, which are helping to develop code. And then you have the system developers who actually build the systems. And again, that's changing because they are now also starting to use co-pilot and co to actually develop these systems. Some of them works out of the box, many other things don't, right? And it's all about how you integrate this like large language models in the right way so that you get actually an experience which doesn't like mislead the customer all the time. And so it's a big challenge still, but like these things are rolling out now, and it's just open the news and you see one after another announced.
Yeah, I think the only thing I'll add to it, yeah, I mean, people have already said it, but like things like natural language interfaces, it largely feels like it's soon to be like a solved problem. Like every system that has had some complex interface that was like only usable by experts is going to now have like a natural language interface, But in terms of that first question that we had, at the beginning of like hype versus reality, I think this is sort of in terms of the use cases and the pervasiveness of it. I think we are in a sort of a hype phase, right now in this. Like I see examples of sort of like things where people have like are taking, like you have like some optimizer for like some system that's tuning parameters or doing like it's solving some combinatorial optimization problem, and they're asking an LLM to suggest solutions to it. And it's basically like, why? I mean, there's like nothing about like the problem structure that like, this thing, like even if it has common sense, like these are not common sense problems. These are like mathematical optimization problems. So, so there's a lot of these kinds of things that I think people will try and eventually they'll give up.
I think there's one interesting question you are raising right now is, so I have no doubt that will change the way people interact with systems. Yeah. And it will have a big impact on it. We just don't know yet 100% how it looks like. What I personally even struggle with is just like, and I think Sam knows it also very firsthand, we have this project together. And like in the end, we want to write a paper about it. We show that a few things work, but it's essentially like a bunch of prompts. Right? You have like, we put this text in there in the following way, and it gives us the right answer. And it was better than putting the text in this way, which didn't produce the right answer. Yeah. It's like, I don't know what our research community means in this new world yet, and how to actually write a good scientific paper which uses large language models. And like, you read these things and said like, Yeah, they tried a bunch of things out. Like it feels like a wet lab. We tried A, B, C.
You tell it slow down, it will then work. Just slow down and think, and it will.
Right, and it's just like I think there's something still not clear on how we actually even publish around that work. What are like the fundamental insights you gain from something? Right now, it's more like, see, we made X happen, and it kind of works. Right, like those are a lot of papers in the space right now.
Yeah.
So, Evan, I also want to say that, I mean, you are talking about automation. And actually, to me, the thing that is way more interesting than actually doing things that we cannot do. Like, it doesn't matter how much it's not about automation. It's really going beyond what humans can do. So just to give you an example, what if AI started generating things that we don't understand? And this is not like hypothetical. Like I was showing, like we are generating these EEG signals. Now, even the best EEG specialist cannot tell from EEG that someone has Alzheimer's or someone has Parkinson's. So how can, if an AI generates an EEG signal for someone, how do we know whether it preserved the actual underlying physiology of this individual? And if it did, how do we know what structure there is that allowed it to be, this is the EEG if an Alzheimer person and this is not? So AI is getting, so one way to answer the first question, how do we know that it preserved it? We probably, like one approach is to train another AI model to say, okay, so can you detect who has Alzheimer, who doesn't from EEG signal? And if the generated signal gives you equal efficacy or efficiency, equal accuracy as the ground truth data, then at least it has the same power still from an AI perspective. But we don't know, like we can see that it has the same power, but we don't know yet how did it generate it, and what is the thing that we generated indirectly with our machines?
So my first encounter with computer was in 1964 when I joined IIT as a freshman. And it was a punch card computer, and I went and typed an equation, x squared plus 2x plus 1 equals 0. And I was very disappointed that it could solve it. Right? So at that time, I had no idea what an algorithm is, that you actually have to tell it how to solve it and so on. But now we are living in an era, you can go to an LLM model and just give it the equation and it will solve it. I mean, this is fundamentally different. This is fundamentally different, and most of us can understand it because we understand the evolution and what happened. But I just keep wondering what will happen. I mean, if many things like this start disappearing, from teaching and so on, then, I mean, Tim was saying that interfaces are so different now that we think of systems differently.
It's a very interesting question. I mean, the SQL question is it's like, why are LLMs so good at generating SQL queries or Python programs? Well, they're so good at it because they've been trained on a billion examples of it, right? So, like, I mean, what if people stop writing SQL queries? Then does what is it going to be trained on? It's a weird. Yeah, exactly. You'll be frozen in time in a weird way. Yeah. I don't know.
Question, sorry. So it always surprises me that the best scientists and the best mathematicians, best authors have only...
I have to say one thing, which is actually pretty funny. Like, I take your question in a second, but like Sam's point, like frozen in time, so we released a feature called Generative SQL for reInvent, and it went live in preview. And one thing which we forgot to do is actually tell it what the current date is. So as part of the prompt, so if you ask like what was your sales yesterday for that schema, it was always putting in the same date when the last day was when the data was trained on. Of course, like a big uproar, but this was something which we haven't considered, as we had it right for our training data, but not like in this part. So we needed to fix it, and the fix is out now, so like it doesn't happen. And I can talk about it, but it's just like to your point, right? Like the model was trained for a particular date, and that was the date the model memorized. So sorry to interrupt you, but go ahead.
It's along the same lines. So the brain is able to do so much with a fraction of the training data, fraction of the energy used, right? We about use 100 watts, our entire body, right? And that's pumping our heart and using our brain and all these things. But we have to spend so much time in the training, right? We have all this energy, all these GPUs. How much, for me, it seems like there's so much room left in figuring out what the right architecture is and auto ML and all these cool things. But everyone's just like big data, better model. And for me, it's very surprising. So I want to know your guys' thoughts on that.
I think it's a. I mean, again, I don't think any of us is exactly an expert in like training these things, but it's exactly what Tim said. It's just, you know, people are following the thing that works the best, right? You know, so it's not that people aren't trying to build simplified, reduced models that have comparable performance at, you know, a lower training cost or a lower inference cost. It's that they keep losing when they try, you know. I mean, it's like the you know, and everybody's, you know, it was 2 years ago, 3 years ago, it was, oh, the context windows aren't going to scale. We're going to have to do these interesting, you know, new architectures to get beyond this. And yet, you know, it's like they've just continued to figure out how to make the things bigger and better and faster. And I mean, I think it's all about, you know, what performs the best in the end. But
yeah, if any of the systems people are too good, they will keep basically like building systems that, you know, give you bigger capability. And until that stops, until you hit some like fundamental limit there, I think, at least in the industry, like, you know, there's a race to kind of build the best things, and this is the path that's winning.
I mean, the other thing though that occurs to me is it's not like humans. I mean, you're right that a human for inference at like runtime, my runtime cost is 100 watts, but the integrated, you know, energy that I consumed and the amount of time it took for me to get to the point where I am, where I can sit up here, you know, it was at least, you know, 14 or 16 years of training time that it took before I was able to have a conversation like this with you, right? Before I, you know, grew to an adult, right? I mean, so that's, you know, it's a different pace of training and a different type of training, but you know, maybe it's actually not.
If you want to add that, but you have to like add all of evolution, and
right.
Then it's
plus I benefit from like, you know, right, millions of years of architectural evolution of brains, right? So
I mean, like.
Yeah. Right, exactly.
The other issue is just like training those things are so damn expensive, so people are not really willing to take a lot of risk every single time you train one of them. And it's just like in training, we talk about partially years by now, right? So like you do a bet, you bet on something which is like, oh yeah, that probably should scale up. And then you still have an army of people doing nothing else than trying to keep that on track. And then you have another army of people who actually give thumbs ups and thumbs downs for the answers, right? Don't forget, every single time you train one of them, there's an army of people sitting somewhere, Philippines and co, typically, which do nothing else than evaluating these models and do the fine-tuning in the end by human evaluation. Right? It's a huge thing and really, really, really costly. So you don't do big bets. It's like if you develop a car, you do something where you think like, oh, they all look kind of alike, right? And in the moment they don't, it's a big risk factor.
you got to go.
I need to go.
Thanks, everyone.
Happy American citizenship. Yeah, congrats.
Yeah, go ahead.
Yeah, use the mic, please. Thank you.
Okay. So
Yeah, I think he's going to ask at the mic.
Good. Okay.
So as you were saying, the computations are expensive. So what's your view on sustainability of these computation resources? Like whether, like, as we know, distributed computing and edge computing are definitely a solution. is technologies like quantum computing, like which can optimize like how we store the data and how we use the data, can also they also help? Like, are they coming? Like, what's your view on that? That's my question.
I think quantum computing could optimize many things, but that's gonna take a long time to wait for. So I think there are many things. So I think actually the biggest problem is not like the architecture and all of that stuff is not like the general models are very successful. But I do think that energy consumption is a big, big problem. And you can see it. I mean, we probably all felt it, like you know somehow that ChatGPT is getting dumber and you are limited to like a few queries and all of that stuff. It's so expensive. I mean, the people who make the money on it are the cloud producers or the cloud providers. So there is a need to reduce the energy consumption for the inference and the training. But I think the inference also even more so if you want to use these models effectively. And that, I mean, quantum computing, once it happens, that would be great. But maybe I would think even before that, maybe some analog models, like the brain is much better at using energy. Analog models are much better at using energy. So that probably is some intermediate path.
Manya, do you think, I mean, do you think optical is like, do you think optical computing or this optical domain stuff could eventually get to the point where you could do serving of something as large as an LLM with it, or?
I totally agree with Dina that the energy question is very big and there is this urgency of solving. And quantum is a bit in the realm of Star Trek. It's a little bit too futuristic. My hope is that photonic computing is an intermediate step to jump from digital to photonic and then to quantum. That doesn't mean that it's a very quick replacement, especially we need to figure out a way of changing data or being able to consume analog data. Data in the world is analog, but the way of years of computing evolution kind of trained us into thinking of data as digital formats, and we haven't really solved this barrier yet. Our current photonic systems still treat data as digital. I think the next big problem that we need to solve is how to take analog data, like video. I mean, our eyes are taking data or cameras are all taking data in analog format. How can we feed analog data into an analog computing system? Hopefully once that problem is solved, we are one step closer to having true analog systems.
Sure, I don't know if we had a question back there, I think one more, and then maybe Arvind.
Since Arvind's asked more than one, I'll ask more than one, okay. This has been touched on a number, what I'm about to ask has been touched on a number of points, where we're sometimes surprised or oftenly surprised what large language models can produce. Sam was mentioning this. And Dina mentioned how in her work she's used a number of different architectures in her system. And the evolution of these architectures, whether in specialized contexts or in the large language model context, and there seems to be a lot of what I'll call engineering insights that happen, where transformers and self-attention is very hot now, and it had evolved over time, and how you architect these different components, these networks, seems to be as an engineering or experience base. So my question is there a theorem here? Do we have any level of abstract insights that could guide us?
So, I mean, at least in my, so the word that I work with is, like, I'm focused on medical problems. So I focus on the problem needs to be solved. It's less so if what is the architecture, and you are limited by the data, where the data is available, the differences between different data sets that you are pulling together to make a higher inference. So there is, I mean, I understand that you are, like from the previous conversation, is that we were talking about general architecture versus like, is there more development on the architecture side? Like, okay, what comes after diffusion, for example? I mean, I think these architectural things are not going to come too often. Maybe like we're gonna see, of course, at some point something after diffusion systems, but it's not like the old days when like every year there is the best and the next architecture. To me, there is still a lot of space about how do you combine not necessarily architecture but systems. So even if all of these neural networks are using transformer, that's not the point. The point more that they have different data and different outputs, and because you are limited, so one of the things, for example, that there are like already like trained model, like some people now use ChatGPT to generate input to feed them to other models and to leverage all of the stuff, or use LLM or some data set that trained, the model got trained on that data set, but they don't have access to it. Now they are using that model, combining it with another neural network, combining its output, and with another neural network to feed yet a third neural network. So there are going to become a lot of these, like, how do you combine systems of neural networks that each one of them produces something, has access to a certain data set to train on it, and has certain objective and feed them from each other and grow a much more powerful system. But it's more about the combination, the boxes and their interfaces and their data than the whether it's transformer or like diffusion or whatever it is.
To this question of like, is there a theorem? I think it's very interesting. I think there are certainly a lot of people working on it. Yeah, absolutely, no, absolutely. I mean, there's this is not, I think, what I do, and I don't think anyone kind of here really does. But there are people that are working on basically a theoretical understanding of these architectures. It is, but I think your observation that it's a very empirical driven, like the state of the art is very empirically driven. The biggest advances are not yet coming from those theoretical insights. They're trying to explain things that basically people have already seen empirically, which has happened in a lot of areas. Like actually in our field of networking, I think this is largely how theory has contributed. It's always kind of after the fact, people have already, designed things, the internet kind of works, and now like, okay, let's try to understand, put a model to it and see if we can kind of say deeper, why should it have worked? Why was this algorithm actually so effective? And that's, I think, happening in the neural network. But if you look at the theorists, they're like, 10 years behind. So if you look at advanced like transformers, diffusion, GANs, these are coming from some insight. It's not like people are just trying random things, but it's not coming from things that they can always prove that, it's sort of an idea that people try and it works, and then it takes a life of its own.
I mean, I think there's the other question that's very interesting from a theoretical perspective is like, how do you get any guarantees if you start using these things in the core of systems in some way?
Wasn't this always the question about computer systems? I remember when I started as a graduate student with systems, and it's like, okay, so there is theory, and people want always to have
prove
theory,
that it's going to be
something about
correct or
systems.
something. Right.
Systems people don't care to think of it as an art. And
yeah, that's what I'm saying. We're pretty comfortable with this.
I feel like to me,
not chapter.
To me, large language models, even for somebody like me who's probably never proved a theorem in my life, like or never a real theorem, the squishiness of LLMs makes me kind of uncomfortable. Right?
Yeah,
I think that are really interesting because, again, working a lot in the medical field. So you would think we all take drugs, and you would think that these drugs, a drug is really, in some sense, a poison. When given in the right context at the right dose, it is beneficial. but it has all the side effect of it, and for some people, it's just pure poison. And you would think that we really understand, and those people who, like, there is a huge, like, very detailed science, but really drugs are approved and based on, like, statistical, like, empirical evidence. And even when we think that we understand what we call the mechanism of action, I just give you an example, antidepressant. We understand some form of the mechanism of action, like how it acts is like, okay, it like changes the way the cells or the neurons uptake the serotonin, for example. That's an explanation of how to. Why is this related to depression at all? Nobody knows. So these explanations and thinking that really science knows exactly how every step is happening is just a form of being comfortable with the science. We are typically comfortable as long as we have some abstraction, we can move from some abstraction to the next level of abstraction. And I think there's something very similar in machine learning. We have some understanding about the models, how they work, what kind of like conceptual guarantees we believe is feasible, but at the end of the day, it's empirical evidence. You hope that it is also statistical evidence so that you can guarantee a form of generalizability.
Right, but the proof is in the pudding, as they say, right? I mean, it works. Right? I mean, the same is true for, I think that's a good point about the internet and other things, like it works. I mean, whether or not you can prove that it works or when it'll work, but you know. So, Arvind, you want to get the last word? We got 4 minutes left, so.
Dina, you talked about your device, Emerald, was it? It's collecting all kinds of signals, right? So are you also trying multimodal models, right, to analyze disease or anything?
Yeah, so the way I think about it is really at machine learning at multiple levels. So the first level is that if you can non-invasively and without asking people to change anything about their life, you can get their physiological signals. Now, the second level is I don't care where these physiological signals came from. I don't care whether the respiratory signal came from chest belt or whether the heart rate came from your Apple Watch or from the Emerald device or whatever. Now, let's look at these new opportunities from the fact that we have all these physiological signals that are tracking the dynamism of the organism and extract higher level information about diseases. So yeah, the more modalities you have, definitely things get more powerful.
All right, I'll ask one last question. What is the role of academia in the world where all of the big systems and all of the big models are owned by a small number of companies? I mean, especially these days with the turn to cloud computing, and it's like, you know, essentially all the big interesting networks, all the big database systems, and now all the large language models are owned by, you know, 3 or 4 companies. So like, what's our role?
I can start with that. So I think it is true that developing AI and driving the AI effort is being dominated by the bunch of hyperscalers. And maybe our role in academia is to provide alternative perspectives and diversity in terms of solutions and ideas. Most companies have a fixed charter and they tend to look at short-term goals. And perhaps this is an opportunity for us to think about more long-term impact of AI, and we can afford to be wrong in the bets that we place. And so maybe this is where the college, with its interdisciplinary approach, becomes very effective at fostering this AI technology.
I mean, I think your question is not just hard question, it's also, it's sad, like, depending on your like, what you believe is going to happen in the future. I think it's very limiting if really academia doesn't have the resources to train powerful models to, I mean, even if we have the ideas, if the ideas was require hundreds of millions of dollars and that funding does not exist, it doesn't matter how good the idea is. And you can just like make the model bigger and the data set larger and trumps any idea. But the thing, I think one thing that academia still naturally has, which is it can be a neutral partner. Because, I mean, all of these companies, of course, they are competing companies with competing goals. And so one thing that helps academia is that it is a place that can bring these players together to provide a neutral environment where ideas can be developed for the interest of all, like the companies themselves, the society, and everyone. So this is one thing that academia, and I think MIT traditionally has excelled at doing. But there is no doubt that academia is losing a lot by the fact that the resources do not exist, and it's very, very hard to bring to the academic context.
Yeah, I think ideas will always matter. I mean, so even, you know, even this thing that I said, like, yeah, there's, you know, the generalist kind of approaches, you know, to many problems, and I think that will definitely continue. But it sort of doesn't mean that there are some fundamentally hard problems in all of these things that you know, industry will continue to kind of innovate on, and academia will innovate on. Sometimes, if you can't try things out, that's a big barrier. So maybe, and we are seeing this. You know, you'll see greater kind of collaboration, you know, between industry and academia. I think a lot of us already kind of do this, you know, to basically to overcome this type of barrier. But I don't see really a world where you say like these ideas don't matter. You know, the other thing I kind of, because we talked about this, you know, large models, large-scale data solving problems kind of a lot. One thing that I found very interesting just in seeing just what happened with LLMs is it's like once people know that something is possible, all of a sudden there's a lot of creativity and like other better ways of doing it. So, you know, once people saw like what, you know, the Chat GPT, the first version could do, it took, you know, 6 months before you started seeing these kind of papers that said, oh, we can kind of get you on any metric that you want, you know, something that gives you comparable, you know, behavior, but is a much smaller, you know, model. Some of those sort of maybe cheat in some sense because they use that thing to give you training data for their smaller model, but that's actually quite an interesting path to making things more efficient, right? So there will be, I think, you know, there will always be a push towards kind of, you know, efficiency, reducing power, you know, making things smaller. But if you're like thinking like, what's the thing that's driving like the state of the art in capability? Right now, it is basically these larger and larger architectures. And everything that they prove can be done, I think you'll see just become much more efficient over time.
I'll just say one last thing, which is to answer my own question. I think, you know, I look at my amazing colleagues on stage, and they have, despite the challenges of, you know, an industry, you know, they've all managed to have actually quite dramatic impact on the way that industry works. You know, and you look at, you know, some of the big ideas, whether, you know, it's you know, Tim's work that, you know, getting all this learned stuff deployed in Amazon, or Manya's, you know, all the people who are using Manya's optical networking ideas. You know, it's ideas do win, and, you know, people, it is still possible for academia to have a big influence on things. And you know, I'm not an expert in LLM architectures, but, you know, I suspect that there will be a role for academia. I'm sure there will be a role for academia to play. So anyway, thanks very much, everybody. We're out of time, but I really appreciate you all hanging out. I hope it was enjoyable, and yeah, till next time. Thanks, guys.